everybody. Is It's on. It's working okay. Yeah, that's perfect. So good morning, everybody. Again, like everybody else, it's a pleasure to be here this morning. Some really, really interesting speakers this morning. It was certainly a learning experience for me on a lot of it. The talk that I'm going to give it this morning is really around manufacturing and industry, and how the use of VR, AR, digital twins, and AI impact on manufacturing. So, I'm a local lad, so I'm born and bred in Dundalk. In fact, I served my time originally in the building to the left of the studio here in PJ Carroll's tobacco manufacturing company. And then I came to DKIT to study mechanical engineering. I've been in mechanical engineering for 40 years, automation, specifically robotics, for the last 30 years, having set up and ran the robotics business for ABB, and then in 2014, setting up and running for Kuka Robotics. I'm passionate about manufacturing, and for that reason alone, I sit on a number of boards, including the IBEC Industries Board, the Irish Manufacturing Research Steering Committee, Industry Steering Committee, the AMTCE, which is the Advanced Manufacturing Training Centre of Excellence. I sit on the Board of Governance there, and I also sit on the NSAI Robotics Steering Group. So, a little bit about Kuka. So the company is more than 125 years old. So you can imagine it's not 125 years making robots. In fact, it's 1973 when Kuka made the first industrial robot on behalf of Volkswagen, on a commission from Volkswagen. 15,000 people worldwide, more than 50 different countries, 100 different locations. It's about a 4 billion euro company. So it's reasonably large. It's made up of 5 different pillars. One specific pillar that we're going to talk about later on, but the robotics pillar is the one that I work for. And what we do is we supply the robotics and software hardware to our system integrators, system partners, and machine builders in each of the countries that we operate in. We also have a systems business, but that operates at a very large level. So systems business, and Timmy may already be aware of it because Volvo are a customer of ours, but this is where we will build entire automotive lines or aerospace lines or nuclear systems or modular house building and so on. So these are typically systems that run from about 10 million up to several hundred million. We have the digital pillar, and this is what we're going to talk about in the next series of slides, but we have visual components, device insight, and mosaics. And then we have specifically in warehouse and hospital automation, we have Swisslog. And Swisslog do distribution centers, logistics centers, but they also do transportation systems and pharmacy dispensing systems within the hospital environments. As I mentioned, we're over 125 years old, but it's the bottom paragraph that really capitalizes what we do. We embrace innovation and deliver engineering excellence globally. Yeah, but it's combining mechanical engineering expertise with software and AI-defined infrastructure capabilities. So when I joined the company, or even 20, 30 years ago, Kuka would have been known as a mechanical engineering company. Nowadays, it's really very much known as being a software and AI company with a mechanical element to it. And this is the start of it. So when we talk about our digital sphere, we're talking about the applications that we have in around the robot application software, simulation, our knowledge databases, remote service, device connectors for the various different machines. But a lot of this is platform independent. So we have mosaics, which is around about collaborative planning software. So that means, it's independent. So we can interface and collaborate with multiple different third-party vendors. So the likes of Dassault Systems or Siemens PLM and so on. The visual components is when we're talking about entire factory design. So digital twins of entire factory layouts and plants. The Kuka is when we're talking about the Kuka Sim and Kuka Sim Pro, and we're talking again about either cells or factory layout or virtual commissioning, offline programming. And then we have our device insight, which is around the actual operation of the factory. So this is where we can digitally connect all the robots and machines. We can pull all the data from them that influences the machines of the future, the robots of the future. It allows us to do predictive maintenance. It allows us to calculate the energy that we're using through the machines and how to improve on that. Now, when we talk about digital twins specifically, we're talking about the Kuka sim and we're talking about cellular type design. So we can take robot cells, we can design them up, and then on the visual component side, we can design the entire plant. So we can build those two together, but they are compatible with each other. The Kuka sim side focuses on the robot cell. We can calculate out our exact motion paths. It's very accurate. It's using a virtual controller, so it's not close or thereabouts. It's exactly what you're going to get in the real world. It allows us to calculate the energy consumption, reachability, and so on, the functionality of the cell. The visual components allows us to focus on the production hall, the generic manufacturing. So we can pull in other machines. You can pull in injection molding machines, you can pull in presses, conveyors, etc. And we can calculate the times around all of those machines and then allow them to interact with the robot cells as well. So that allows us to have a holistic material flow analysis and KPI-based measurements and targets. But why? What does it all do? So what it does actually is it allows us to save planning time. So from initial concept through to final design, we can reduce the time that it takes to actually design the concept and build the final solution around it. It allows us to check the feasibility and the viability and verify digitally what the machine is going to look like when it actually hits the factory floor. It allows us to calculate what a change upstream or downstream will make on the entire process. And eventually, what that means is when it drives up revenue and it reduces our costs. If we can take a machine or a plant layout and we can verify it digitally before it's ever cut or before it's ever made into the real world. On an automotive line, we can take 6 months out of the delivery of a line. And that is a huge amount of revenue. And then we're using extended functionality such as modeling, connectivity, arc welding, amongst others. There are various different toolkits that we use around the digital twins. We have the Kuka sim for the 3D simulation and offline programming. We have Work Visual, which allows us to configure the controllers and the machine data, online connections to the robot controllers. And then we have Office Light, which allows us to do the simulation of the real robot controllers and the offline programming and virtual commissioning. So that all allows us to enable a seamless workflow really between the virtual and the real world, your digital twin. If we take the AI element into it, so when we're talking about robot programming, you're talking about coding, but we're trying to get away from that. So using AI, we can use chatbot functionalities. So we can tell the robot what we want to do. If it's a very simple application like palletizing, let's say we're building a pallet of boxes of butter, and we want to build a grid layer of 6x3. We can tell the robot what we want to do. We can give it the dimensions in a chatbot and tell it that we want to do a layer of 6x3. We want to have 6 layers high, and we want to have interleaves between it. And we will generate it. So we're getting to the point of low code, no code programming for robotics. We can export it to VR. So again, in terms of a lot of what we've seen already, if you're walking around, the factory in the real world, you can see where all the problems exist. If you've already designed it digitally and you can export it to VR, you can now walk around your factory before it gets delivered. You can see exactly where problems might crop up or might already exist. You can check it for the ergonomics of the machinery that you're building and designing. And you can use it as a tool because a lot of these lines take a year, 2, 3 years to actually deliver. So you can use it as a training tool for your staff as well. So they can actually virtually walk around like the DAA example. So you can actually walk around the shop floor before it becomes a real shop floor. and we have mixed reality. So Mark gave a very good, concise example of, or description of what mixed reality is, and that effectively covers what I'm saying here as well. So you actually have reality, then you have augmented reality, you have your virtual world, and you have augmented virtual world, which gives us extended and mixed reality. Now, why would we use that? There are multiple reasons why we would use it, but one reason is around safety. So obviously the safety of the human in the loop is of paramount importance. It's the most important thing with any machine design, but particularly around robotic machine design. And what that allows us to do is to create virtual zones around certain elements of the robot cell, whether it be the tooling or even external components within the robot cell. So it could be the machine that we're interfacing with. It could be an injection molding machine, or it could be a laser marker or whatever. But these are all expensive pieces of equipment. We don't want to damage them either. The human takes priority, but we don't want damaging the robot. We don't want damaging the equipment. So we can build all these virtual safety zones around it. And then we can export that into the mixed reality, and we can take it on our handheld devices and walk around the shop floor where we're going to be putting this robot cell. In this case, it's a virtual robot cell until we get the approvals on it, but we can check out all the various different safety elements around that. This is just an example of when it's working through it. It's just going through the various codes. You see the various different spheres that are showing on the robots. But these are virtual cells that are being built up. And they're overlaid on the shop floor as you're walking through it. You can import any simulations coming from your simulation software package. And again, you can walk down on your shop floor and you can overlay it on the real world. That helps you check for the physical size of the cell, how it's going to run when it's in operation. You can get your operator buy-in. You can do your training, your offline training. And you can do that from, as I say, from your handheld devices. If you want to try the mixed reality yourself, you can scan the codes here, depending on whether you have an Android or an Apple store. But you can download it and try it out for yourself. There are a number of examples already on it of various different robot cells. And as you walk around the arena here or in the exhibition hall, you can take your example and you can see how that would overlay on the real world. So what's next in terms of what we're working on? So if we talk about the NVIDIA Omniverse, there's lots of companies now starting to roll this out. And we're no exception of being able to work with NVIDIA to be able to move forward on our digital offerings. So what that allows us to do is to program and simulate our robots within the NVIDIA Omniverse platform. The operators can monitor and control the robots from anywhere as long as they have an internet connection. And then you have your virtual training environments within the NVIDIA Omniverse. So that's for your operators and technicians to be able to familiarize themselves and train themselves before the equipment actually arrives on site. So thank you very much.